This isn't just a first for India, it's a first in lunar exploration. No one successfully landed near the moon's south pole before.
India is the first country in the world to land a spacecraft near the moon's south pole, a moment of history for the country.
Chandrayaan-3's revelation has sent an electric pulse through the global scientific community and beyond, the kind of revelation that redefines how we see our nearest cosmic neighbor. At the moment of its seemingly routine lunar descent, when all eyes were fixed on another technological marvel unfolding in silent twilight, Chandrayaan-3 uncovered something that no one anticipated, an entirely novel lunar feature of breathtaking and unsettling proportions. A cavern cavernous in both literal and metaphorical terms opened up beneath the lander's path, a chasm so profound and so unexpected that it transformed the serene powdery gray of the lunar landscape into a geological apparition that sent shivers through even the most seasoned scientists. Before we start, smash the like and subscribe buttons for more updates. It was the kind of discovery that could not be credited to a glitch, misread data, or visual distortion. The lander's instruments, built and calibrated with infinite care, performed flawlessly. The descent camera captured image after image of a near-vertical trench, its walls dropping into an abyss that defied depth measurement from the surface. As Chandrayaan-3 executed its soft landing just meters from this abyss, the sensors registered a sudden anomalous thermal signature emanating from its depths, a stark contrast against the uniform lunar cold. The steadiness of the moon, long assumed to hold its mysteries in silent dormancy, seemed at that moment to betray a murmur of ancient, cryptic energy deep within. Scientists hurriedly transmitted the data back to Earth, and what came across were readings both haunting and exhilarating. The trench's temperature did not simply reflect residual heat from solar exposure. It was distinct, warmer, as if something below lay in a condition far removed from the lifeless chill expected in such barren ground. Speculative debates ignited around whether this warmth hinted at residual volcanic activity, pockets of volatile compounds, or even geophysical processes that had eluded all prior lunar missions. The global choir of experts, from volcanologists to geologists and cryophysicists, found themselves grappling with an unexpected lunar drama that demanded rapid, unprecedented collaboration. There was a surreal poetry in the way this discovery unfolded. A lander designed to study the lunar South Pole's regolith, elemental composition, and seismic characteristics inadvertently stumbled upon this subterranean enigma. It was as though the moon, long perceived as a silent, dead witness to cosmic history, had whispered suddenly, and in a voice far more complex than we ever imagined. Overnight, the cratered gray surface that shaped our expectations became a canvas of hidden dynamism, a place where the dormant might still stir. The implications are vast, both scientifically and philosophically. On a strictly scientific level, such an anomaly forces a re-evaluation of our understanding of the moon's thermal and tectonic history. For decades, lunar research relied on models of a geologically inactive satellite. This trench, with its anomalous warmth and precipitous descent into darkness, suggests that even today, beneath the lunar surface, there may linger pockets of heat or residual activity, vestiges of a tumultuous past, or pockets of remnant geophysical energy. Could there be subsurface magma reservoirs still cooling slowly? Heat channels deep beneath the regolith, perhaps preserved by insulating layers that slowed their decay? The data demands rethinking of crustal models and encourages further spectrometric, gravimetric, and thermal probes into the hidden architecture of lunar geology. Beyond pure geology, the discovery carries haunting implications about the possibility of volatile retention on the moon. Something beneath the trench is warmer. In cold vacuum, warmth implies some kind of energy source. That raises the unsettling and thrilling prospect of trapped volatiles, possibly water ice warmed and mobilized, or even rare concentrations of exotic gases released slowly from deep reservoirs. The presence of such compounds, held in subsurface pockets, could revolutionize lunar resource science. Water, now warmed slightly by subsurface warmth, might exist in accessible forms, valuable not only to scientists hungry for knowledge, but to future explorers seeking sustainable operations. It provokes the notion that future human outposts could tap into hidden caches, drastically reducing the logistical burdens of lunar settlement. Moreover, the thermal irregularity hints at dynamic processes that might still be active, albeit slowly and sporadically. the moon's interior may not be as inert as previously believed. Could there be microseismic shifts deep below, heating the trench's walls? Might tidal flexing, influenced by Earth's gravitational pull, stir internal friction that periodically releases heat into select zones? If so, we may need to revisit our perception of the moon as a monolith of quiet eternity, and instead regard it as a body still breathing faintly, shaped by ancient energy yet lingering in slow circulation. It's a subtle reminder that planetary bodies don't always follow the tidy decline into stasis we expect. On a broader cosmic scale, this unsettling yet electrifying event reshapes our comparative view of planetary satellites and rocky worlds. If the Earth's moon retains vestiges of internal heating, even in isolated pockets, what might that suggest about other seemingly inert bodies across the solar system? Mercury, Ceres, and the crops of moons orbiting the gas giants might harbor similar surprises. It encourages a wave of renewed scientific curiosity, as researchers refocus their attention on dead worlds that may not be as dead as they seem. In turn, missions to other rocky bodies may be reconsidered to include instruments sensitive to these subtle thermal anomalies, to seek signs of hidden activity in places where none was expected. Then there's the intangible impact, the way such a discovery connects deeply with our collective imagination. The global reaction has been electric. Among everyday enthusiasts and professionals alike, there's a renewed wonder in the moon, not just as a cratered companion, but as a world of riddles, perhaps still alive in its own discrete fashion. Art, literature, and popular culture will inevitably respond. Scenes of astronauts peering into yawning subterranean chasms, of thermal mists rising from moonscapes, will circulate across creative platforms. This is no mere plot device. It is drawn from the bedrock of real, astonishing science. It brings the moon out of the textbook and into the realm of living myth. Chandrayaan-3 didn't set out looking for a cosmic thriller. It brought one. The event stands as a testament to the unpredictable poetry of exploration. It is a reminder that in space science, even meticulously planned missions must allow for the capricious revelations of the universe. The lunar trench's warmth is a summons to humility. Even the bodies we thought we knew well harbor secrets that can shock and inspire. It also creates a pivotal juncture for policy and planning. Space agencies and governments will need to calibrate their strategies to build instruments capable of deeper thermal sensing, more precise subsurface imaging, and in situ drilling. Upcoming missions to the moon could be retooled, targeting this trench or seeking analogs elsewhere on the surface. Private space enterprises and international consortia may collaborate to design probes or rovers capable of descending into the abyss, sniffing its plumes, sampling its walls, feeling its heat. It redefines the technological frontier, not rockets, landers, or orbits, but the detailed, granular exploration of hidden worlds beneath familiar surfaces. At a human level, there is something profoundly poetic about it all. A probe, so small in the immensity of space, descended upon the moon's face and found beneath it something alive with questions, heat, mystery, potential. In that moment, the pale moon became a dark cave of secrets, as if our cosmic neighbor were holding its breath, inviting us to peer deeper. The scientific endeavor, in all its precision and planning, met with the raw surprise of nature, and together they created a new chapter in humanity's lunar narrative. The discovery marks a fissure not just in the lunar crust, but in our assumptions, our methods, and our dreams. It beckons us forward, deeper underground, into darkness that may glow faintly with answers. It urges us to treat even the most barren landscapes as worlds rich in possibility. In the quiet of space, Chandrayaan-3's unexpected trench stands as proof that even when we know the terrain, the universe can always surprise us. And as the data continues to pour in, our minds race not toward conclusions but toward questions. What exactly is causing that warmth? How deep does the trench go? And what lies at its base? Are similar features scattered across the moon, invisible to satellites but alive with heat? Could we one day send a probe down that void, watching it light from within as it descends? For now, those questions echo across mission control rooms, university labs, and the cafe conversations of curious minds. The shock that rippled globally is settling into something more potent, a restless curiosity that drives the engines of exploration onward. The chasm revealed by Chandrayaan-3 quickly became more than a geological oddity. It transformed into an intellectual crossroads where multiple disciplines converged in urgent fascination. What began as a sudden anomaly in thermal readings and surface imagery rapidly evolved into a deep scientific pursuit. The very geometry of the trench demanded precise mapping. Orbiters already in lunar orbit were retasked to focus high-resolution cameras and spectrometers on the coordinates transmitted by the lander. This was no simple photo survey. It involved sweeping the surrounding regolith for subtle albedo variations, dust trails, and fractures that might hint at the trench's origin story. The targeted orbital passes revealed a structure unlike any other prominent lunar depression. Craters are common. Volcanic rills, though rarer, are known. This formation defied such categories. Its sides were sharply defined, suggesting a relatively recent collapse rather than a slow erosion over eons. The floor was obscured by darkness deeper than expected, absorbing light rather than scattering it in the typical lunar manner. That peculiarity suggested that the bottom was not simply dust-laden regolith, but perhaps a more compact, non-reflective material, or, intriguingly, an opening into a void that swallowed incident light. The mere possibility of a hollow subsurface area immediately ignited speculation about vast lava tubes or even a network of ancient conduits running beneath the lunar crust. The measurements also indicated that the walls of the trench exposed layers of rock not previously accessible to study. Such strata could be the key to reading the moon's internal history, each layer a page from an ancient archive stretching back billions of years. Geologists were enthralled by the opportunity. If samples from varying depths could be retrieved, they might reveal not just mineralogical compositions, but also isotopic ratios that would clarify the moon's formative timeline. This, in turn, could refine theories about the moon's origin, whether from a colossal impact with early Earth, the accretion of primordial material, or a hybrid of competing models. Attention quickly turned to the trench's thermal mystery. Remote sensors were calibrated to detect the exact nature of the warmth. Was it uniform throughout the abyss, or concentrated in localized pockets? Was it constant or variable over the lunar day-night cycle? The first datasets suggested irregular distribution, almost as if there were conduits or channels directing heat to specific points. This irregularity hinted at either ongoing subsurface processes or non-uniform materials that retained heat differently. Scientists proposed deploying a network of small penetrator probes around the trench to measure temperature gradients and seismic activity in real time. Such an arrangement would provide the first three-dimensional thermal and vibrational profile of an active lunar feature. Meanwhile, mineralogists studied spectral data from the trench walls. Certain wavelengths indicated the presence of compounds rarely found in the open lunar regolith. If verified, these could be signs of materials preserved from deeper within the moon, shielded from solar radiation and micrometeorite bombardment for eons. Some minerals exhibited hydration signatures, which was startling in a location so far from confirmed polar ice deposits. Hydrated minerals could suggest ancient water rock interactions deep beneath the surface, interactions that might have persisted longer than current models predict. As this scientific frenzy unfolded, space engineering teams began sketching the technical outlines of a descent mission into the trench. Rovers capable of handling steep, jagged inclines were conceptualized alongside tethered descent modules equipped with advanced illumination systems. The engineering challenges were formidable. The moon's reduced gravity offered some advantages for climbing and anchoring, but the lack of atmosphere, the potential instability of the trench walls, and the uncertainty of its depth presented daunting risks. A mission would require innovations in autonomous navigation, debris detection, and possibly aerial mobility using compact, low-thrust propulsion systems designed for vacuum. From a planetary science standpoint, the trench opened a unique window into comparative geology. On Mars, long volcanic rift systems and collapsed lava tubes had been documented. On Earth, tectonic forces constantly reshaped the crust, burying older features. The moon's trench, however, offered something different. A pristine collapse event, unaltered by weather, tectonics, or biological activity. This preservation made it a near-perfect case study in extraterrestrial geological processes. By comparing its form and composition with similar features on other bodies, scientists hope to untangle universal principles of crustal behavior across the solar system. Another angle of inquiry revolved around the possibility of preserved ancient environments within the trench's lower depths. In the absence of solar radiation and protected from micrometeorites, deep sections could harbor volatile compounds or even delicate microstructures. Microscopic formations created by geochemical reactions long ago. The tantalizing thought arose: if life had ever found a way to persist on or in the moon, such sheltered pockets would be prime locations for evidence. This was not a suggestion of living organisms, but rather of fossilized microtextures, mineral patterns, or isotopic anomalies that could hint at chemical pathways once active in the moon's deeper layers. Astrophysicists weighed in as well, noting that the trench could hold clues to the moon's magnetic history. Samples extracted from deep, undisturbed rock could reveal remnant magnetism, records of the moon's ancient dynamo when its core was more active. These records could in turn shed light on how and why the moon's magnetic field decayed, which has implications for understanding magnetic field evolution in other planetary bodies. Such insights would influence our broader understanding of planetary habitability, since magnetic fields are a key defense against harmful cosmic and solar radiation. The international dimension of this discovery could not be overstated. Almost overnight, research institutions and space agencies in multiple countries began informal exchanges about how best to coordinate follow-up missions. There was talk of an open data policy for all non-proprietary findings related to the trench, in the spirit of advancing collective knowledge. Yet alongside this spirit of collaboration lay the undercurrent of strategic interest. The potential for resource exploitation, whether water ice, rare minerals, or other volatiles, ensured that the trench would become a focal point in the emerging discourse on lunar governance. Determining how and by whom such features might be accessed in the future would be as much a matter of diplomacy as of engineering. On the ground, so to speak, the Chandrayaan-3 lander continued to function as a sentinel beside the trench. Its instruments monitored minute tremors in the surrounding regolith, searching for patterns that might betray subsurface movement. These vibrations, though faint, were not entirely absent. Occasionally, a short-duration seismic event would ripple through the lunar soil, as if some far-off part of the crust were adjusting under stress. Each event was cataloged and cross-referenced with temperature data to test whether seismic activity correlated with thermal changes in the trench. One of the more provocative hypotheses emerged from modeling work conducted in parallel with observation. Some geophysicists proposed that the trench might be part of a subsurface fracture system connected to deeper reservoirs of trapped gases. In this view, tidal forces from Earth's gravity could periodically squeeze these reservoirs, releasing pulses of gas that vented upward. If these gases carried latent heat, they could explain both the thermal anomalies and subtle seismic signatures. Such episodic venting would be a phenomenon previously undocumented on the Moon, raising profound questions about its current geodynamic activity. The prospect of gas emissions led to another layer of investigation: mass spectrometry of the trench's immediate surroundings. Even in the tenuous exosphere of the Moon, it might be possible to detect transient spikes in certain gases if sensitive enough instruments were deployed nearby. Preliminary modeling suggested that heavier gases, such as argon or radon, might be most likely to linger long enough for detection before dissipating into space. A positive detection would be groundbreaking, potentially offering the first direct evidence of contemporary volatile movement within the Moon's crust. While scientists mapped, modeled, and measured, public fascination took on a life of its own. The concept of a mysterious, heat-emitting chasm on the Moon captured the global imagination. Artists rendered dramatic visions of astronauts suspended over the abyss, beams of light stabbing into infinite darkness. Documentarians began assembling footage, not for post-discovery retrospectives, but to chronicle the ongoing unfolding of the mystery in real time. The Moon, already a symbol rich in myth and meaning, now bore a new chapter, a place where even in the era of high-resolution satellite mapping, raw discovery could still surprise us. The cultural weight of such a discovery extended into philosophical realms. For centuries, humanity's view of the Moon had oscillated between the mystical and the mechanical, between romantic symbol and scientific specimen. The trench blurred those lines once more. Here was a place that demanded rigorous empirical study, while simultaneously evoking an instinctive sense of awe and unease. It challenged the human tendency to see the moon as a static backdrop. Instead, it reasserted the moon as an active player in our solar neighborhood, a world whose story is not yet fully told. From an educational standpoint, the discovery sparked an unexpected surge in interest in planetary sciences among students worldwide. Universities reported increased enrollments in courses related to space geology, remote sensing, and astrobiology. School curricula began incorporating the trench as a case study in how exploration continues to evolve, showing that even familiar destinations can yield unprecedented findings. Science communicators embraced the opportunity to explain complex concepts: thermal conductivity in vacuum, regolith mechanics, isotopic analysis, in accessible terms, using the trench as a captivating entry point. In the halls of mission planning, the discovery became a catalyst for innovation. Engineers re-evaluated the capabilities of current and planned lunar rovers. They explored integrating ground-penetrating radar systems with greater depth resolution, deploying micro-drones for mapping inaccessible voids, and developing robotic arms with precision sampling tools for vertical surfaces. Each proposed technology was not just about this one trench. It was about preparing for a future where lunar exploration must be ready for abrupt encounters with the unexpected. The sheer unknowns surrounding the trench drove home a critical lesson. The moon is not a finished story. For all our orbital imagery, for all the landings past and present, we have only skimmed the surface, literally and figuratively. The deeper we look, the more we realize that unseen processes, some potentially still active, may be shaping the lunar environment in subtle but significant ways. Such a realization compels a shift in perspective. The moon is not merely a stepping stone to Mars or a testing ground for technologies. It is a complex world in its own right, worthy of exploration for its own mysteries. This shift also rekindles the spirit of international competition, though in a context more nuanced than the space race of the past century. Nations with emerging space programs see in the trench an opportunity to make their mark with specialized missions: compact landers, nimble rovers, or swarms of microprobes tailored for high-risk environments. Established spacefaring nations weigh whether to commit flagship missions, with budgets and timelines adjusted to seize the scientific high ground. In boardrooms and parliamentary sessions, the trench appears in discussions about funding priorities, mission rosters, and partnerships. In research labs, simulations attempt to reconstruct the trench's formation. High-powered computing clusters run countless scenarios: a collapse over a void left by cooling lava, a sinkhole triggered by regolith subsidence over volatile rich layers, or even an impact event that penetrated unusually deep, creating a vertical shaft rather than a shallow crater. Each model is tested against the observed geometry, thermal profile, and surrounding terrain. None fit perfectly, which only deepens the intrigue. Speculative yet scientifically grounded theories emerge that perhaps the trench represents a convergence of multiple processes. An ancient lava tube whose roof thinned over time, weakened further by micrometeorite impacts and microseismic vibrations until it gave way in a sudden collapse. If true, it would be a unique hybrid formation, one that could reveal stages of lunar geological evolution in a single location. As weeks turn into months, Chandrayaan-3's role as the silent observer at the edge of this abyss grows ever more significant. The instruments continue to feed the steady stream of data, building a temporal record of the trench's behavior. Subtle changes are noted: minor shifts in temperature gradients, slight alterations in regolith patterns near the rim, variations in reflected light that suggest small landslides or materials shedding into the depths. These details, while minor individually, could cumulatively outline a living portrait of the trench's ongoing evolution. The trench's emergence as a focal point for lunar science began to redefine how mission planners thought about proximity operations on extraterrestrial surfaces. Traditionally, landing sites were selected for their relative safety: flat terrain, minimal boulder fields, predictable lighting. Chandrayaan-3's experience proved that even these safe areas could harbor profound, unpredictable features with immense scientific value. This led to a subtle but important shift in approach. Future landers might deliberately target zones where orbital data shows anomalies, rather than avoiding them. The aim would be to balance safety with the potential for transformative discovery. In response, engineers and scientists collaborated on conceptual mission profiles optimized for rapid investigation of unexpected features. One idea involved equipping landers with deployable tethered sensor pods designed to be lowered into vertical voids like the trench. These pods would carry cameras, spectrometers, thermal imagers, and environmental sensors, able to operate autonomously in complete darkness. Another proposed system featured microclimbers, robotic units with spined wheels or gecko-inspired adhesive pads, to scale trench walls and collect targeted samples from layers otherwise inaccessible. From an orbital operations standpoint, the discovery reshaped how mapping satellites prioritize their data gathering. Instead of sweeping vast regions uniformly, there was a push toward dynamic targeting. If a lander's surface instruments detected something unusual, thermal anomalies, unusual seismic signals, orbital assets could immediately adjust their observation schedules, directing more passes and finer resolution toward the coordinates in question. This integrated feedback loop between surface and orbital platforms could become a standard feature of future lunar exploration architectures. In scientific circles, there was an eagerness to apply emerging technologies like quantum gravimetry to the trench's environment. Quantum gravimeters, sensitive enough to detect subtle variations in gravitational pull, could help map the internal structure of the moon beneath the trench. Such mapping might reveal voids, denser rock formations, or even moving masses of material. Understanding the substructure would be critical not only for geological interpretation, but also for assessing whether the trench posed any hazards to future explorers or installations in the area. Meanwhile, the trench sparked a wave of comparative analysis with other planetary bodies. The European Space Agency's Mars mission planners examined their data for analogs, vertical shafts or collapse features with unexplained thermal properties. On Mars, such features might serve as entrances to subsurface refuges potentially capable of harboring microbial life. The Moon's trench, while not a candidate for life in the same way, still offered a valuable analog for understanding how planetary crusts behave under certain conditions. This cross-planetary thinking enriched both lunar and Martian exploration strategies, highlighting the shared lessons across worlds. The presence of exposed strata in the trench's walls attracted interest from cosmochemists intent on studying the record of impacts preserved in the layers. Each stratum could contain spherules or shock melt fragments from ancient meteorite collisions. By dating these inclusions and comparing them with known cratering records, scientists could refine the lunar chronology, narrowing the margins of error in the Moon's geological timeline. This would also help calibrate the impact histories of other bodies in the inner solar system, since the Moon serves as a relatively intact witness to the solar system's early bombardment. There was also a growing awareness of the trench's potential role in studying space weathering processes in a protected environment. Normally, the lunar surface is constantly exposed to solar wind and micrometeorites, which gradually alter the chemistry and appearance of rocks. The trench's lower depths, shielded from direct exposure, could preserve materials in a less weathered state. Comparing these samples with surface equivalents might reveal exactly how and how quickly space weathering changes mineral properties. Such insights could be invaluable for interpreting remote sensing data from other airless bodies. As these scientific opportunities multiplied, so did the engineering challenges. Thermal control for instruments operating in the trench was a primary concern. The temperature differentials between the sunlit rim and the shadowed depths were extreme. Any probe or rover sent inside would need to manage transitions from blistering heat to deep cold within minutes. Innovations in adaptive thermal insulation and variable emittance radiators began to emerge from early design studies, with potential spin-offs for spacecraft and satellites operating in other thermally volatile environments. The trench also became a proving ground for advanced autonomy in robotics. Communication delays between the Moon and Earth meant that any descent into the abyss would require onboard decision-making capabilities. Rovers or climbers would have to assess wall stability, choose sampling points, and adapt routes without waiting for instructions from mission control. This requirement dovetailed with the rapid advances in AI-assisted exploration systems, which could learn and adapt based on real-time sensory input. If perfected, these autonomous systems could later be deployed in even more remote and challenging environments, such as the icy crevasses of Europa or the cliffs of cometary nuclei. From the perspective of human spaceflight, the trench posed questions about astronaut safety and training. Should humans one day explore its depths directly, they would need specialized equipment and procedures. Tethered harness systems, portable lighting arrays, and compact drilling rigs would be essential. Training environments on Earth, such as volcanic caves or mine shafts, could simulate some aspects of the experience, but lunar gravity and the absence of atmosphere would require unique adaptations. Such preparations would inevitably spill over into broader lunar mission readiness, making crews more versatile in handling unexpected terrain. An intriguing line of thought emerged regarding the trench's potential as a natural radiation shelter. Cosmic rays and solar particle events are major hazards for astronauts on the moon's surface. The overhanging walls and depth of the trench could provide significant shielding. If stable ledges or chambers existed within its structure, they might serve as temporary refuges during solar storms. This possibility added a layer of strategic value to the site, potentially integrating it into plans for sustained human presence on the moon. The thermal anomaly at the trench's base continued to be a subject of intense modeling. Some researchers began considering the role of phase change materials beneath the surface, compounds that could release or absorb heat as they change state in response to pressure or temperature variations. If such materials were present in significant quantities, they might act as a sort of thermal battery, charging and discharging over long cycles. This could explain why the warmth persisted in a location otherwise dominated by extreme cold. As the mystery deepened, the discovery began influencing mission priorities beyond the moon. Proposals for small-body exploration missions started incorporating the capability to investigate vertical features, from asteroid fissures to cliff faces on dwarf planets. The logic was straightforward. If a vertical void on the moon could hold such scientific riches, similar features elsewhere might yield comparable surprises. This represented a subtle but meaningful expansion of exploration philosophy, broadening the focus from horizontal traverses to vertical excursions. If you like this video, please give it a like and subscribe to our channel. Also, leave your comments below and tell us, what are your thoughts on Chandrayaan-3's shocking moon discovery? We want to hear from you. Thank you for watching, and see you next time.